We're now going to consider how to draw free body diagrams. Free body diagrams are very useful when you're dealing with forces. So a free body diagram shows all the forces that are acting on a single body. So let's draw a free body diagram now for a body with two forces acting on it. So we'll have the force F1, which is equal to 3.0 newtons in the I direction, and F2, which is 2.0 I plus 2.0 J newtons acting on the body. So in this case, the free body diagram looks like this. Now the arrows on the free body diagram represent these forces. The direction of the arrow shows the direction that the force is acting, and the length of the arrow shows the relative magnitude of that force. So in this case, force 1 has a magnitude of 3 newtons, while force 2 has a magnitude of square root of 2 squared plus 2 squared, which is approximately equal to 2.8 newtons. So in this case, force 2 has just a slightly smaller magnitude than force 1, and so it's represented by a slightly shorter arrow. Let's have a look now at a practical example of how we can use free body diagrams. So what I have here is a series of 3 hanging masses. So what we can do is, if we didn't know the center mass but we knew the other 2 masses, we could use a setup like this to work out what is the mass of this unknown hanging mass in the middle. So how we do that is with a free body diagram. So let's draw our free body diagram now. So we're drawing the free body diagram for this central hanging mass here. So it has got 3 forces acting on it. It's got its own weight force, which we're pretending is an unknown force. So this weight force is acting vertically downwards. It's then got these 2 tension forces from the strings acting on it. Now the size of the tension force is given by these other hanging masses, as they are what is generating the tension in the string. So in this case, the tension in this string is caused by 300 grams of hanging mass. So we could calculate it as just G, 9.8 times 0.300 kilograms. And this one over here is 250 grams. So again, this tension is just caused by that weight force, so we can calculate it as 0.250 times 9.8. Now, from Newton's second law, we know that all these forces acting on this central mass here must sum to 0, as our central mass is not accelerating, it's not moving. So now that we've drawn our free body diagram, we can move the forces around to join them head to tail. And when we do that, we can either use a ruler, if we've drawn it properly, to scale, to measure the length of the weight vector here, and from that calculate what it is, or we can use a bit of trigonometry to calculate the size of the weight force. So I'm going to leave that as an activity for you to do now. I've included the angles and the weight forces on the screen, and your task is to calculate the weight of this central mass here. So with the vertical, we've got an angle of 40 degrees here and an angle of 60 degrees on this side.